the book has the whole complete derivation. This is the displacement-based energy for a laminate. You can take it for granted or follow the derivation. The main thing is what in an isotropic material would involve it's always a product of stress times strain that goes into the energy, and that, if you do it in terms of displacements, would be epsilon squared over, no? You would have terms like Young's modulus times epsilon squared. And you know, for example, that epsilon x is du by dx. So you would expect to see a du by dx squared term. There it is. And there should be the equivalent of a stiffness here, which is the A11. Now, this is stiffness per units of Newton per meter instead of Newton per meter square. So it's stiffness times length because it's already been integrated once. Remember, energy is a triple integral dx dy dz. So if one of these has already been eliminated, then instead of having E involved in the integrand, I will have the A matrix. So this top line involves the terms that we would consistently know to find in a plate problem in isotropic material in a membrane kind of situation. The bottom, very bottom one, which involves now the curvatures, there is an equivalent to this kind of derivation that usually we know it in terms of m squared over 2EI if it's a beam. And again, this is integrated over the length of the beam. Or instead, I can write my moment as a d times d2w dx squared term. Moments like mx is d11 d2w dx squared with a minus sign and so on. So from isotropic materials, we know that the energy would involve terms like this. In anisotropic, I would expect to have terms like this, which means I have the second derivatives of w squared, which you can see are there. And then I have a d, which in an isotropic material is E h cubed, the thickness of the plate, over 12 times 1 minus nu squared. So if you're doing an isotropic material in bending, there is a term that will always appear, which is the d, the so-called d. The corresponding one now, because this is squared, and there's one over here dividing it, you can see that the corresponding term will be the d11. So if anybody has seen the metal expressions, these are equivalent and analogous, but they are not easy to derive if you don't start from first principles. Membrane energy, so energy stored in extension, in plane shearing or contraction of the plate. Bending energy stored in bending in any direction or twisting. And then the coupling, which is the green mess in the middle, which involves the B matrix. That's the one where you actually combine now in-plane displacements, U and V, with out-of-plane displacement W. So while the top line only involves the in-plane displacements U and V, and the bottom line here involves the W displacement, in the middle we have them combined. And you can see how that really complicates things and why it's very advantageous from a mathematical algebraic perspective to actually have a B matrix equal 0. That's the general expression if it's in terms of displacement.